while she's messing with this, it's kind of interesting. You know, I had a long career in the industry, and I didn't start out, you know, working on high frequency devices. I started out as a chemist at Beckman Instruments in processing. So it was interesting when I moved to McDonnell Douglas. I worked on all high frequency stuff. I was their program manager for the F-18. That's where I learned about. I was surrounded by electrical engineers, and those guys talk a whole different language than chemistry. So it was interesting. I worked for them for quite a while, and then I moved over to Faro Corporation, and then finally ended up at AGC. I've been a product manager now for good Lord, 20 years. So all I've been doing is, and product managers, all we're worried about is relationship. How do we intercept with the customer's needs? Customers change their needs over time, and we have to be ready for them. So we have to product managers direct R&D back at the home base. Okay, we all done, Rachel? Okay, okie dokie. All right, so let's see if this works. So, oh darn. It doesn't work. Ah, there he goes. So I wanted to, I only have 30 minutes to talk, and I could throw a lot of slides in here, but my talk today is going to be basically, we're going to address it in two parts. The first part will be what is the market? How big is the market? Where is it going? And what are the needs of the market here in the future? I will also then break it into the second part, which is the materials, glass, which is near and dear to my heart. So just to give you an inkling of what's going on is, you know, the 3G, 4G, 5G, and 6G is one of the largest markets, but it's pivoting now. Most of the people who are using 5G are looking at glass as an antenna in a package or antenna on glass. So to take your pick. So your AIP or AOG you'll hear that term from time to time from a lot of folks. The 5G and 6G, the engineering is still in flux. It's going to take another 10 years before it really becomes, it really gets rolled out. 6G is a whole different problem. It operates at 95 gigahertz up to 1.3 terahertz. So the engineers don't even know how to measure it because most spectrum analyzers only go to 125 gigahertz. The NIST guys may have a higher frequency spectrum analyzer, but I haven't explored that yet. Semiconductor chips, everybody was talking about it yesterday. So, you know, you start breaking down the semiconductor chips and you got AI, cloud computing, automotive, IoT. So every chip is different for that particular application. Glass plays a predominant factor in automotive and IoT. Excuse me. The automotive guys, most of what we're doing with those guys is antennas. So AGC has a factory in Chihuahua, Mexico. We're #1 manufacturer of windshields in the world. There's no one close to us. So we manufacture the glass that goes into the windshields, and we manufacture the windshields in Chihuahua, Mexico. But we have a design center that actually designs the antennas that go into that for 5G and 6G. 5G right now has been the challenge for us. And so our design center is located in Ypsilanti, Michigan. Say that 2 times. And then finally, architectural glass. Architectural glass represents a novel generation of glasses for us. We actually can change the glass surface properties, what we call meta lenses. I think you know, some of the folks have talked about it. So the next generation of technology is meta lenses, and it's actually used in a lot of different applications, including high frequency applications. It's going to be used in LiDAR because it actually, time of flight with meta lenses is very important for automotive applications. So that's all glass based. So just a real quick, you know, where is this all going? Basically, you know, high frequency is driving the density of, you know, the number of antennas that are out there. Just a quick factoid is there's 400,000 cell towers in the world, and they're approximately a kilometer apart. Because of the 5G operates at sub-6 and a little bit above 16 gigahertz, the distances between the cell towers have to shrink. Actually, they have to be no further apart than 300 meters. That quadruples the number of towers. And actually, that's good for us, more glass. So there you go. All right, so I heard a lot of stories about, we compete, I don't compete with the glass manufacturers, I compete with PCB. PCB has been around for more than 70 years. It's got billions and billions of hours of reliability, and the cost is in the dirt. So, typical pricing for PCB in the 510 to 515 panel size is about 1.5 cents per square millimeter. And that's with 2 layers of RDL, copper filled, and a couple other things. So glass is approximately running around 8 cents per square millimeter. So but it hasn't reached the volumes that PCB has, nor it's a trade-off in performance. So you're looking at performance versus cost. PCB has a lot of things that don't work well at high frequency. And I won't touch on that right now, but I will give you some information. I'll talk a little bit about the materials end of it. But the pricing is the biggest issue that we have. And then the adoption rate of using glass is based on legacy. PCB is pretty robust. It's got, it's pretty flexible. It doesn't break, but glass does break, and you have to be very careful in how you handle it. So the largest PCB manufacturers, are in China and in Taiwan. So they're just now working on smaller form factors, and the 510 by 515 form factor is now just starting to see the daylight. Excuse me. So here you got just a chart, with the, you saw Dr. Nelson talk about the insertion loss, which is on the y-axis, and then dielectric constant is on the x-axis. So copper clad laminate is a little bit above 0.001 at 10 gigahertz. Fused silica is in the dirt. I mean, it's really low. And it actually has been tested out to 100 gigahertz. But I got a chart showing that what the quartz looks like at the higher frequencies. So this is basically a modem. And the antenna is that you see, we're right here right now. 5G, where's my laser? Hey, right there. So we're right here at 4 to 6 gigahertz. At 28 gigahertz, the CCL and glass are competing head to head, but above 28 gigahertz, then the antenna needs to have glass, low loss glass, not just regular glass. Quartz is too expensive. Quartz is at 200 millimeter wafers are running between $70 to $100 a wafer. And you can only grind it down to maybe 300 micron. Everybody wants 200 micron. So quartz is too expensive. So the agency is working on the next generation of glasses. Actually, we've rolled them out already, which actually has low loss and low price. Price is king. Price drives everything. So you can have greatest performance on the planet, but if you can't sell it, it doesn't go anywhere. What I heard yesterday, and this is just an aside, was that technology could supplant employment. That's the furthest thing from the truth. So I got a paper that I received from Accenture that actually says that the contrary, technology will drive employment. It will actually drive GDP and will actually result in a higher employment than what's previously thought. So you can read the chart. I don't have to tell you about it, but it actually counters what I heard yesterday. So technology drives employment. So the global artificial intelligence, this is the chip market that we're working on. It's quantum engineering. It's high frequency. It actually has a lot of different facets to it. So, but this is just the size of the market, and by 2030, it's going to be pretty good size. And I've seen a range, and that's $160 billion. So I'm sorry I didn't put the units there. My apologies. Okay, so we're going to start to move into the materials end of this. So one of the things that we work on, we're on architecture. We supply architectural glass for all the buildings in the world. We have a couple other competitors in this field, but what we're working on is what we call fixed wireless access points, which actually allows the beamforming technology to hit the point in the glass and allow a signal to pass through it. Glass is not sodium-containing glass. It's the cheapest glass, but it also attenuates the signal. So you have to have access points to allow the signal to penetrate through the glass and go into what they call a customer provided equipment that's inside the building, which allows you to have Wi-Fi. This technology is metal lens. So this is, some of the newest technologies that AGC is actually developing to provide high frequency applications. So this allows a signal to pass through. At 28 gigahertz, it becomes really problematic because buildings are shield the signal. This is just a chart, how big it's going to be, and the average selling price. The average selling price is dropping pretty quickly. So our profit margins are going to remain high for the next 5 years or so, but they're going to drop pretty quickly. So, we're always working on profit margins, the start, maturity, and then the end of life. This is just a promo, so we work with Docomo back in Japan. They're a big, telephone company. So we actually developed and tested some of our metal lenses with these guys. It worked really well at 28 gigahertz. I think Benson will send my presentation out to you all, so you don't have to worry about copying or taking pictures. So my second part to my presentation is about materials. So I'm just going to go quickly through the materials end of this. And if you have, we can hold your questions to the end, and I'll answer your questions to the best of my ability. Okay. So one of the things about glass is that it's based on SiO, Si, and the sodium-containing glass. I've heard some of the silicon guys who say, "Oh yeah, it'd be a great material if it's just silicon." So, but silicon's lossy. Silicon glass non-containing alkali systems don't perturb the signal. Sodium-containing glasses do perturb the signal, so we don't use many sodium-containing glasses in high-frequency applications because of the attenuation of the signal. We can adjust the glasses by function, compositions, surface properties. Surface properties are becoming the most important part of glass and high-frequency applications. Glass is pretty unique in its ability to withstand high temperatures and allow us to do nano texturing on the glass itself, which we can create lenses on the glass. So we're actually approaching nano level. The guys who do DNA diagnostics, that's all nano level stuff. So, it's the DNA is approaching, is one of the smallest features right now that we actually supply glass to. And that's just not glass, that's quartz. Quartz is preferred because one of the other properties of quartz is its autofluorescence. I don't know if you know that if you shine a light at 355 nanometers into glass, it actually activates chromophores, which actually radiate back the light. That's a bad thing. For a DNA, you don't want that to happen. You want to have the lowest autofluorescence possible. Quartz has the lowest, as well as a low, loss. So, what's needed for glass? CT is probably one of the most important things, especially if you use it as a carrier or if you use it as glass core. So you got to match the silicon, CTE, because if you don't, then you get stress in the package, and then it actually reduces the reliability. At 10 gigahertz, 28 to 100, and 100 to 1 terahertz, the loss of the glass is important for most of the electrical engineers. INEMI has also approached us, and they want us to supply them the physical part of the electrical properties, which we have. We have a lot of electrical properties on our glass, and we feed it to the electrical engineers, and they design with our electrical properties. And we've measured it over and over and over again. So we use a lot of instrumentations. We've also gone to NIST to help us with some of this. So it's 10 years, 15 years ago, I went to NIST to have them measure the loss of quartz, and it's so low that the instrument that they had on the bench couldn't measure it, so they had to go to another instrument. So measuring loss is a tricky thing. Okay, so the three main applications for glass is glass core, carrier, and glass components, and each one has its own unique set of characteristics. Glass carrier, you have to meet the CTE of the glass, so it doesn't work when you actually mold it. So the glass, and glass carrier is also needs to be matched to the molding compounds that are needed. Then you release it, and then you use the glass over again. Glass core actually becomes part of the circuit, and it actually has to match the RDL and the active devices on that. Also, glass core can also have passives and a couple other items. So CT becomes really important. Glass components is another application that we're working on. Glass components such as antenna in a package or antenna on glass. So every one of these has their specific needs, their specific system requirements, and so the engineers, request a lot of information from us. So CTE is one of the most important parts of a package, and there's a variety of CTEs available. So you can go from, but you see there's a transition point at about 7, 6. So you go from a non-alkali material to an alkali material. Remember, any alkali that's in the glass attenuates the electrical signal. So you cannot have alkali materials in it. We call it non-alkali, but there's a small percentage of alkali for forming glass. It's about 2 to 3%. The alkali containing glasses are around 20 to 40%. So they really attenuate the signal. So attenuation is caused by the electron clouds in glass. So as the signal goes through the glass, it gets absorbed and desorbed by the electron clouds in the glass. So what's interesting is that most of the engineers are down around here. So that's the sweet spot. And then most of the guys like to have 3.1 to 3.6 CTE. This is chart I threw in because I'm always battling PCB. I'm always battling PI. I'm always battling. So this is the dielectric constant and insertion loss of polymers. Polymers are great at the low frequency and they're cheap as dirt. That's one of the nice things about polymer and PCB. They're cheap. However, at the higher frequencies, they start to break down. And they got a lot of electron clouds that are loosely held. And so they change their dielectric constant and insertion loss. Engineers have battled this for several years by putting in tuning forks or tuning circuits, excuse me. Tuning circuits cost money. So now they're starting to migrate towards more glass-based products. The system, using glass in the higher frequencies makes sense. It's the supply chain that actually is slowing the production rate for glass. Dr. Nelson showed us chart. I threw this in, Shelby. I wanted you to see this. So Dr. Nelson showed a slide this morning about quartz. No quartz is exactly the same. There are two methods for making synthetic quartz or quartz. One is called the direct method, and the other one is called the indirect method. The indirect method is the blue line, and the direct method is the red line. As you can see, the dielectric constant insertion loss is very, very low and stays very, very stable at the higher frequencies. And you can see that the bandpass filters here perform very well. So we control the amount of change in the slope of the line is controlled by the contaminants in the quartz itself. So if you can control the contaminations in the quartz, you control loss. That's it's for everything, glass, PCB, everything. The electron clouds actually dominate what causes loss. So, excuse me. The industry has always stayed on wafers, and the reason is silicon is wafer. It's 200 millimeter or 300 millimeter, and a lot of the folks are using 150 millimeter. But as the world has started to adopt glass, people are starting to convert over or transition to panels. Panels have a better yield than wafers. So most dies are square or rectangle. So if you have a die that's 5 by 5 millimeter, then your yield rate in a round wafer is around 65%. That's a loss. That's a lot of material to lose. In a rectangle panel or square panel, yields are approaching 85% to 90%. And the difference is not 100% because of the streets. You got to factor in the loss of material there. And then there's the exclusion zones that you have to factor in as well. So, so we're migrating to, actually the industry is standardized on PCB, which is 510 by 515. Glass is being standardized on that format as well, 510 by 515. So especially at 200 micron, most glasses are now approaching 200 micron thick. Most of the engineers like 200 micron thick for a lot of factors. This is just to echo some of the things that Dr. Shelby talked about. This is just some of the TGVs that are out there. I don't know if you know this, but AGC actually drills, we drill our own TGV. So these are just some of the straight shapes that we drill. So it's just, just some of the things that we actually do. And, a lot of there are two types. There's X shape, what we call hourglass, and then there's taper shape. At a higher frequency, the taper shape is preferred. I'll show you, I got a piece of data I can show you about that. This is just the different types of metallizations that are out there. So we have conformal, we have full filled to partially filled. And then here are the S21 curves that are associated with each of those different types of fill. So as you can see, the full fill is probably the best in S21.23. So it works really well, and most of our customers prefer full filled. However, the issue is copper needs a seed layer, and the seed layer is probably the most critical link of putting copper into the via. And someone said the reliability. How do you determine the reliability? It's driven by the seed layer. So the seed layer and the amount of voids in the copper drive the reliability, and also the most important part, the resistance of the via. At a high frequency, you want a totally transparent electrical signal going through that TGV. Okay, so the next question I heard today, and I threw this chart in for him. I don't remember who asked it, but the reliability of the copper in the via. This is 1,000 cycles. 85 minus 40 to 85, and the electrical resistance didn't change. And this, I threw in another chart here, which shows the interposer versus glass versus silicon oxide or silicon. So you can see there's a big difference in S21 curves. Again, this is open public information, and I'll be sending this presentation to Benson. Okay, so it's the little things that affect performance. It's just amazing how small and subtle things can be, especially as the frequency goes up. So we're starting to see weird things at the higher frequency. At 28, 35, 50 gigahertz, we're seeing skin effect problems that we never had before. We're seeing that the taper affects the electrical performance. So this chart here, we did a measurement on this, and it was actually done by Dr. Sato-san, which is one of my colleagues back in Japan. So he did this work back when he was at Georgia Tech. So it's interesting to see how the taper does affect the electrical performance. It's just not the glass, it's the entire system. It's glass, it's copper, it's the surface, it's everything. Okay, so I'm starting to see a crossover. What's interesting, and this is 10 years out, 5 to 10 years out. So I'm starting to talk to the engineers about photonics, and we're starting to talk about how do we actually integrate photonics into a circuit. So photonics in a circuit, PIC. They love the acronyms. So we're starting to see hybridization of electrical circuits with photonic circuits. So it's still a long ways off, and it still may be several more years before you even see a device that incorporates photonic devices. Oops, did I do that? So one of the problems that most of the engineers they're running into the power wall, meaning that as the frequency goes higher and higher, they got to pump more energy into the system to throw the signal further and further, and that's running into some severe heating problems. Glass is not very conductive. It's 1 watt per meter K. PCB is even worse. So how do we handle that? Well, it's all these nice schemes, thermovias, and just all these different types of schemes, but it all adds cost. So the elegant solution is light. I'm a baby boomer, so I went to Disneyland when I was 12, and they had the laser with the modulation, you could talk to people could talk through lasers. So yesterday's technology, tomorrow. That's my saying. It's Disneyland too. Anyway, so this is just I put this together from a couple of sources. It doesn't abridge my NDAs, but it just shows you a caricature of what some of the chips and some of the circuits will look like in the future. So this is optical hybridization. One of the big companies in this area, and that they actually work on this type of thing, is Samtec. And I don't know if some of you know them or not know them, but they're actually one of the companies that actually work on photonic devices, and they have their own photonic labs as well. And this is just another caricature of glass core with photonics and waveguide. So yesterday I saw a poster with someone was writing of making waveguides in glass. Of course, it was my competitor's glass, not mine, but that's okay. So it's interesting to see that lasers are actually going to dominate the field in many, many ways, both in communication, writing, for waveguides, and also for communication. And I think that's about it. So the fabric of high frequency is probably coming to a nexus point, because we're seeing automotive guys. They need antennas in their windshields. They need heads-up display. They need to have low latency. We're seeing the wave of high-frequency products that are coming down the range or coming down the pathway now. At the higher frequencies, 28 gigahertz, they have no options. We're running into serious issues with attenuation. The scalable or form factor is that we have to meet costs. You cannot adopt something that's too expensive. At 8 or 9 cents a square millimeter, it's just too expensive. No one's going to do it. So it's got to get down to around 3 cents per square millimeter. And finally, the integration of chips will arrive sooner than later, especially as the guys start to build modems that actually go into 55, 60 gigahertz range. And that's the end of my talk.
Thanks, Howard. Yes. So we have a few minutes for the questions. Anyone? So our next guest, Dr. Kyu-oh Lee, he will be joining us remotely. So Dr. Kyu-oh Lee is from Intel, and he is an electronic packaging technology expert with over 14-year experience in developing advanced packaging technology at Intel Corporation. He is responsible for enabling packaging solutions for Intel Foundry service and developing packaging roadmaps and architectures. He has expertise in technology development of materials, chemistry, and equipment for advanced packaging, including embedded multi-die interconnect bridges, system in package, and embedded coaxial magnet composite core inductors, and thin film capacitors. He received 2020 Intel Achievement Award and has authored over 54 internal patents and 38 technical papers. Dr. Kyu-oh Lee has MS from Korean Advanced Institute of Technology and a PhD from UC Berkeley. So with that, we invite Dr. Kyu-oh Lee to talk. Thank you.
Thank you for kind of nice introductions. Good morning, everyone. So my name is Kyu-oh Lee. As the chair mentioned, that I'm working for Intel Foundry service and providing the packaging solution for the Intel Foundry service customers, and also enabling the OSAT ecosystem within US and also outside US for Intel wafer. Given that now, like with IFS, we need to enable the OSAT, the packaging solutions for Intel wafer, not like the integrated design manufacturers. And I'm excited to present advanced substrate roadmap for heterogeneous integration roadmap on behalf of the HIR single and multi-chip chapter 3. And today's like majority contents will be based on the 2021 the HIR roadmap editions. Okay. So this is the outline of the presentation today. First, I'll talk about the demand of the, just wait for a second. something wrong. Yeah, the demand for the compute, especially the high performance computing and artificial intelligence, and how heterogeneous integration will play a role in keeping up with this compute demand. And second, I'll briefly talk about what is the pros and cons of heterogeneous integrations. What will be the key technology enabler to achieve the comparable performance to the monolithic integrations? And moving forward, I will kind of address the advanced substrate roadmap, and also the building block that we propose all our industry develop in a few key attribute area that's shown below, like ranging from the patterning design rule in high-speed I/O and bump pitch and power delivery and form factor and outcome. And I'll wrap it with the summary. So when you look at it over, this is like the report by the OpenAI. The AI, the training runs has been increasing exponentially with just based on these estimations, about 3.4 months doubling time. Obviously, this is faster than the pace of Moore's law, which is typically about 2-year doubling period. So certainly you can see that the compute demand is outpacing the compute capabilities that we have. That means I think we should do something beyond transistor scale to keep up with the compute demand. Traditionally, or typically the whole mathematical calculation that are needed in AI, the floating point operation has been used as a key metric to assess the compute power. And that is actually simply a function of the single process clock speed, the cycle, which is typically about 4, and the clock speed, which is ranging from about 3 to 5 gigahertz, and the number of core. Typically there is a limitation in increasing the clock speed due to some physical transistor limit. And then I think the most efficient way to improve, or maybe cost affordable way to increase the computing power is simply the increased number of the core or transistors. But when you look at it in this, the state of our product that is in the market, like a Google TPU, Intel Ponte VQ, they are already reaching to the full the radical die size. And with increased the cost due to the lower yield, especially at the advanced node, the increasing die size is not really preferred solutions from the total cost ownership perspective. Thus, I think it is quite imperative to move from this monolithic the packaging to the heterogeneous integrations of multiple modular dies. Heterogeneous integration provides greater flexibility in terms of total computing area and mix and match the different functional die and have a faster total time to market, and then a lower total cost of ownership compared to the monolithic packaging. But heterogeneous integration required additional die area for the die-to-die interface. It also poses a lot of additional technical complexity since it has many interfaces to deal with. And also there are a lot of thermal and mechanical challenges as well. So to achieve a compatible performance, the monolithic integrations without increasing the additional die or minimizing the die area increase, it is quite essential to develop the high density interconnect for the die-to-die communications at a lower power. I think that is a key kind of the vector I think we all need to kind of focus in enabling it. So let's now talk about how the substrate can enable that. I think one of the key metrics for the advanced substrate is the pattern, the capability. So the in the current roadmap now in 2021, when we look at that overall market, right, in the substrate, we can see there are two types of materials. One is like an organic base. The second one is the silicon interposer base. For silicon interposer base, I think the scaling the line in space is much easier, given that we are kind of using the well-established silicon backend now. But for organic substrate, it is relatively challenging since it has to do with additional variables such as like a material shrinkage, topography, and so to continue the scale the line space in the organic substrate, especially the organic substrate typically is in the panel level, like a 510 by 515 or 600 by 600. I think we need to really improve in terms of material wise, we need to improve the topography to kind of enable the enable the fine line litho resolutions. And then one idea also, not only about the patterning capability, the via scaling is quite critical too. So when you look at it overall, all the organic via manufacturing is called like a laser via drilling, followed by the DSMI and ELIS. That actually has a certain limitation in terms of scaling the via. So that's why maybe we can go with some photoimmeasurable dielectric that kind of can much scalable, but it has to have a lower CT to enable a higher number of field layers. And also what we found out was that when you're talking about like a multi-layer in a larger form factor, the very good clean room environment is quite essential too, especially in this kind of litho process. Now, actually, that it can be extended to the other like a wet process as well. Another key metric to define the bandwidth when it comes to like overall bandwidth, this is bandwidth is simply a function of number of wire per millimeter watt unit area length, and times the overall transfer rate. This is critical for not only within package but also all package communications, given that the all package data transfer rate is typically much higher than the die-to-die interconnect. So in general, the network switch is leading the way in the data transfer rate within the package. As shown in the connectivity roadmap, it is expected that the link speed for serial speeds can go up to like a 200 gigabyte bits per second by 2027. I think which is that a significant challenge for the package, especially like organic base and the system design. So the electrical loss are becoming increasingly important as the data transfer rate increase. In terms of overall the insertion loss, there are many components, but I think it's in large, there are two major components. The conductor loss typically is kind of skin effect. The electron transfer through the conductor, and also there's also dielectric loss, the crossover between the layers. So when you look at it overall, it's about enabling this high transfer rate is quite essential to actually enable very smooth copper surface. We target that the roughness need to be less than 100 nanometer case. And also it is quite essential to develop the low dielectric loss or low dielectric constant field of material. But this typically is in trend traditionally we rely on the overall layer to layer adhesion is mainly rely on some chemical bonding or the mechanical anchoring driven by this kind of rough copper surface or rough buildup surface. But since all our direction actually is moving to the a little bit less polarity, the material, the buildup material with less polarity and very smooth copper surface, actually that put a significant challenge in the manufacturing because it is actually high resistance to the dissimilar chemistry. And also it has intrinsically lower adhesion between the buildup copper. So I think it is quite important for our maybe academic industry to develop some kind of pure chemical adhesion based, some adhesion layer in between the copper to buildup or buildup to copper. I think that is quite essential to enable or extend the current organic material for the high frequency data transfer. And another vector, and all about like the interconnect density and the bandwidth of our interconnect density and the data transfer rate channel. The bump pitch, I think it is also play a critical role in enabling the high interconnect density, and also it is very critical to reduce the die area for the interconnect between the die-to-die communications. So we here kind of categorized by the solder-based interconnect and also the hybrid bonding. I mean, there is a clear challenge in scaling the solder-based interconnect, mainly factor that there is some uncontrolled bulging and volume uniformity during the die bond that actually drive this kind of innovative solution like a hybrid bonding, like a diffusion-based bonding. But in general, the solder-based bonding has been well established in the industry more than up to 10 years now. And it's quite cost-effective. And then the solder can act as some amount of buffer for kind of absorbing all the kind of coplanary variations coming from the die and the substrate. But I think it is quite reaching to limit the fact that it is quite challenging to control the volume and so on. So, but I think it is to kind of scale the solder base. I think we really need to improve the overall solder plating uniformity. And also not only the solder, and also we need to control all the kind of variations coming from the die and the substrate as well. It may not be achieved just simply improving the process, build-up process. I think we may need to kind of apply some like a disruptive technology like planarizations. The planarization can be kind of applied in many interfaces, but I think we can choose and the most effective or most cost-effective step. And I think that is quite essential to kind of continue extending the solder-based interconnect. And in terms of hybrid bonding, I think it is relative. I mean, it has been there in the industry for a long time, especially starting from the older CMOS image sensor. Now, industry start to adopt that in the CPU or the AI. I see a kind of still there are significant challenges, especially in the die wafer configurations. Fact that this need to deal with the additional FM or all the variations coming from the singulation, so on. But ultimately, I believe this is the way you can kind of scale the bump pitch maybe below 10 or sub-micrometer bump pitch. And also now we're kind of switching the gear. We just talk about all the overall bandwidth, now moving to the power delivery. I think it's the power delivery is key, also one of the key metric for the performance. The traditional power delivery systems use some off-chip voltage regulators to supply the required voltage and current to the die. This becomes a significant issue, especially for high-performance computing with high total design power. Recently, the full integrated voltage regulators are kind of gaining traction since this enables kind of some dedicated voltage domain, and that require this kind of the integrated voltage regulator inside the package actually require embedding the passive components like capacitors and inductors. But you cannot just simply kind of embed the current the off-the-shelf component into the package because it's quite bulky and all the kind of surface characteristics is not compatible to the current manufacturing system. So not only just from the component side, also we kind of work together with the substrate manufacturing suppliers to come up with some novel architecture materials to enable this embedding the inductor and the capacitor inside the substrate. I think that is another key area we think that is essential for high performance computing. And briefly, I just want to talk about the overall challenge that the industry is facing. As trends scale, we expect that maybe over total die size maybe remain kind of constant. Well, but as I discussed in the previous slide, the compute demand actually outpacing the overall our current capability. So the industry, the way that actually taking is they actually simply increasing the number of die within package that drive the overall package form factor growth and then the layer count growth. They put a significant pressure on the substrate suppliers' capacity. Simply the fact that the overall utilization, we call the panel utilizations, reduced dramatically. So to address that, obviously, I think we see aggressive capacity expansion seen in the industry, but in the same time, I think we need to really also address that. Maybe we may need to increase the overall the panel size or and so on, but they require quite a significant upgrade in the factory tool. And sometimes actually we simply see that the tool actually cannot handle this maximum layer count because it's so heavy. And also these all kind of yield loss is accumulative as we increase the layer count and also increase the form factor. So I think it's yield improvement is quite essential. I know all industries are kind of struggling to that, but maybe we may need to come up with some more aggressive or destructive some yield improvement like a repair or some inline monitoring and kind of inline the repair kind of system to improve the yield. I think that is quite important. And also another key challenge is actually with this all kind of increased layer count and form factor, the technical complexity is actually even higher. Right? We keep scaling the VR, keep scaling the line and space. That actually put a lot of more pressure on yield. So we need some like a more comprehensive approach, like a holistic approach, not like from the materials and tools and factory to have a better yield. So that I think that is the only way kind of address this kind of significant challenge in substrate manufacturing. I think that concludes my presentations. Certainly the demand for the computation is outpacing. the problems that can be realized in the traditional package, which are great. I think it can be overcome by heterogeneous integrations with the faster time to market and greater flexibility and the low cost. And advanced substrate is playing critical role in advanced substrate, a scalable heterogeneous integration package for the high performance computing. And I think we need a greater innovation on substrate, the direct and indirect material process, equipment, manufacturing environment are kind of essential to keep up with the future compute demand. Thank you for your attention. Any questions?
Thanks, our speaker. Any question?
So thank you for your presentation today. This is Jan Vardaman from Tech Search International. So I have a question. When you go to the 3D stacking with the hybrid bonding, because you're taking part of your die and you're stacking the very fine pitch die, then the pitch that's on the bottom of that stack, is that a more relaxed? Obviously, your tight pitch is between the two portions of the thing that you're stacking. But what about the pitch on the bottom? What is that? And does that reduce? Because I'm guessing that that's going to be a more relaxed pitch on the bottom. And that's going to take off some of the pressure for your density requirements on your substrate. Because you put your connections between up in that hybrid bond.
Of course, I think so, right? All substrate is about like a space transformer, right? Meaning that the pitch needs to scale from the transistor and maybe the interposer and substrate and motherboard. So otherwise, there's no meaning of like a space transformer. So it's got to be relaxed. Yeah, got to be relaxed. Yeah.
So then will that help your needs for going to the highest density substrate because you can relax it in that area? Or do you still have the requirement?
Yeah, in general, I guess, I mean, there are many purposes for this dense interconnect, I believe. But mainly, I think the idea is about enabling the high density die-to-die interconnect using the interposer below. With shrinking this pitch, we can reduce the overall unnecessary interface die area. That is one, and the second one is the bottom die actually it doesn't need to be just passive right now. Industry with this 3D interconnect, I think it is more makes sense to have that active die in the bottom. So from that perspective, yeah, I think there's not much harm. And then the bottom die, the bump that facing the substrate below, it can be just regular like C4 bumpage.
Okay, thank you.
Yeah.
Any other questions, please?
Hi, Matt Kelly, IPC. Thanks for the presentation. Didn't really see a lot of discussion in materials development. We know that this is a core enabler in the substrates area. I'm not sure if you have additional information you can share on base material development for build-up technologies.
Sure. So I think I just briefly talk about that. So in terms of data transfer rate, especially for the data transfer rate, I think higher than like a 28 gigahertz. Now I think when you look at the overall bill of material, the dielectric loss is about 0.00, about 5-ish. But when you want to enable that, I think a 28 something gigahertz. Yeah, where is it? Yeah, I think we are targeting that we have to enable the dielectric loss should be less than 0.002. And the dielectric constant is not a really really critical in this like HPC, but we target that the hash should be less than 3. And then and also found out that roughness actually is also kind of start to play a role. The dielectric goes, not the copper roughness. The dielectric material roughness after the dystonia also need to be lower. Traditionally, in our current generation, when you look at in all the product in the market, there is about 500 nanometer range. I think which is very detrimental for the high frequency signal transfer. So the roughness need to be reduced to less than around 100 nanometer range. So that is for the just traditional builder material, and with some older ELIS copper, the web process based process. But I also kind of briefly talk about the photo imageable dielectric material. Industry is developing this material and has been adopted for maybe wafer level CSP or fan out. But I think ultimately it is also kind of good scalable solutions for VIA. If you can adopt the material for the kind of panel level process. I mean, also some limited industry, they actually actively exploring this photo imageable dielectric in the panel level with the conjunction with all the dry process seeding and so on. But I guess the key challenge here, yeah, the dielectric material concern is probably also concerned, but because of the main fact that this doesn't have a filler, normally the CT is higher. For high-end, high-performance computing, typically we are talking about like 20 layers and so on. It is extremely challenging for all the overall package reliability. So the developing of the lower CT, the photo imageable dielectric materials, I think it is also another good way. I don't know whether I answered your questions.
Yes. Yes. Thanks, Dr. Lee, for your time. Please thanks our speaker again. So our next speaker is Dr. Rajesh Vaddi from Corning. Dr. Vaddi joined Corning in 2015 after supporting Corning Flexible Electronics project under a research contract during his graduate studies at Binghamton. He holds doctorate in material science and engineering and master in electrical engineering from Binghamton University. He has a technical expertise in micro and nano fabrication, semiconductor device physics, and glass metal interface interactions. During his time at Corning, he has developed the fundamentals and contributed to technical solutions for emerging display technologies. Additionally, he also developed the fundamentals for the successful integration of through glass vias substrate in packaging technology for high performance RF and power switching products. Dr. Vaddi has 16 published US patents and has been granted 8 of them. He also authored or co-authored 10 referred publications and 9 technical research reports. So with that.
Thanks for the introduction. Good morning, everybody. Thanks for Binghamton University and S3IP IEC for giving an opportunity to share some of our prototype results that we recently accomplished from the Corning R&D Center. I'll be talking about innovative solutions for advanced displays, especially for the microLED side. And also I will speak about some of the 5G related applications and the substrate solutions for that. Here is my agenda, kind of giving a brief overview about Corning advanced substrates that's already existed for different businesses and applications. And I will go through the integration of through glass via interconnects with thin film transistor active matrix display for large area microLED displays. So I'll also talk about aluminum ribbon ceramic, the proprietary process that Corning invented about continuous sintering of ceramic for more suitable for 5G millimeter wave applications, and then give the conclusions. As my previous speakers spoke about, many of them from yesterday, speaking about emerging applications. I know there is a really, really big drive for very complex substrate attributes. So be it a thinner or miniaturization of the devices. For example, for a mobile broadband type of filter designs, you need to have a very thin filters. The substrate have to be very thin in that, and substrates need to be tunable CTE. Dr. Cyril spoke about how the glass composition can be tuned with the CTE, how it matters, alkali and alkali free. Thermal dissipation also one of the very important, given like a lot of high density functionalities on the chip. Now the thermal dissipation comes into big picture. And for low TTV or TPV across the substrate, very useful for carrier bonding type of applications that Dr. Shelby spoke in the morning. And high index glass type of applications needed for AR, VR, and denser interconnects, TGV, low loss substrate for RF and millimeter wave applications. So Cornings have a plethora of substrates in these areas. We possess display backplanes covering from wafer scale to the panel scale for many advanced displays. And we also have a high index glass for AR, VR applications and flexible glass for foldable applications. And also TGVs from many years we are making from wafer scale to panel scale, also available for heterogeneous integration. And luminar ribbon ceramics, that's our new product in terms of substrate space. And also we also have a low loss glass for 5G millimeter wave applications. So I cannot speak about all of those, but I can talk about some of the recent prototype results that we recently accomplished. One of the topic will be for the more advanced display for microLEDs. So we integrated TFT backplanes for a large area microLED display with the TGVs, and we were able to successfully drive the TFTs from the TGV from the backside of the substrate. And also aluminum ribbon ceramic substrates, why they are important for the 5G millimeter wave applications. First, I will go through this integration scheme for the active matrix backplane for microLED displays. So I don't know how much, I'm sure like most of the technology community is following the emerging display, which is now the microLED display. They have a lot of advantages because of the inorganic LEDs, which can operate at a lower voltage. So the overall power consumption will be lower and can have a high color gamut and very high HDR, high dynamic range. And integration of these microLED displays can also give the borderless designs. So especially tiled displays, the individual displays can be tiled into making a bigger display. You might have seen that Samsung came with the wall, which is a 145-inch display. So the one option to realize that kind of a bigger display is to individually tile these displays and then make it really a bigger display. So the problem with that is you can see the seams when you're tiling it. So there is a lot of engineering needed in terms of substrate perspective to hide those seams. And also the other another way of routing the electrical signals that become more complex because now it become a bigger display. So one way to do that is you can seamlessly tile these smaller displays to make a big display. At the same time, you can drive the interconnects for connecting the emitters on TFT backplane on the A side to the IC driver board on the B side using the through glass vias. So where these through glass vias can be. So this can be located along the perimeter of the substrate or perimeter of the tile, or it can be distributed across the pixel circuit for driving the power signal. One advantage with this through glass vias incorporating in the backplane is you don't need to planarly, like through surface, you don't need to route the signals. You can do through the vias now. So it frees up a lot of the real estate on the backplane. So you can include more device functionalities within that. And these through glass vias can be formed before or after or during pixel circuit fabrication. So that, but there are key challenges how to integrate it, because TFT backplanes mostly done with TFT technology, either oxide TFTs or LTPS TFTs, and they come up with a lot of thermal budget. So oxides being going up to 450 degrees C, and LTPS up to 600 to some of the process steps. So there are two different ways. One is TGV first approach. So this is basically you have a backplane. You have a panel, glass panel with TGVs already, and then metallize the TGVs and then planarize them, and then fabricate the TFTs. So a lot of, you might see the issues already here, right? So because metallizing the TGVs, it has to be fully filled. That comes with a problem like thermomechanical reliability, because glass CTE is around, you can tune from display maybe around 3 ppm per degree C, whereas copper is around 16. So eventually when you are subject this whole system to the LTPS fabrication or IGZO oxide TFT fabrication, so they end up like huge stress between the, because of the glass and the metal CTE there, and it kind of create a reliability challenge. So another way is instead of, fully fill the via, you can do conformal filling and then fill the remaining portion of the cavity with the polymer or sol gel type of chemistries. But it also comes up with, you need to have a barrier layer to coat on top of it. Now you have to control the barrier layer with a different expansion of the sol gel or the polymer in the middle versus the metal on the side wall of the via. So we are still working on it, but it's a very risky approach, and very complex steps need to be solved. The second approach is about TFT first approach. So this one comes up with, you take a panel, now you create a blind via in it, and you have to know the known depth of the blind via. So yeah, the second approach is TFT first approach. Now you create this one, you take a glass panel and you create a blind via with a known depth, and then keeping the other side of the glass surface very planar, untouched. And then you fabricate the TFT backplane on it, either it's LTPS or oxide TFTs. Now, since you have only blind via there is no metal involved, so you don't see any reliability challenges there. Then you fabricate the LTPS and then open up the via with the Corning's proprietary process. Then after opening up, we metallize the via conformally that connects with the TFT backplane. And this metal also can be accessible from the B side of the substrate, which is connected to the IC driver board. So I'm going to show some of the results of this TFT first approach in this presentation. So there are a few steps that we need to really control carefully. One of that is the blind via depth. So now we are talking about thousands of vias across the panel. So the control depth of blind via is very important, because we have to open all those 1,000 vias after the TFT fabrication. And the second one is when you are fabricating the TFT, it's not like a pattern registering to the pattern. It's like now TFT pattern is registering to the TGV pattern is registering to the TFT pattern. So the TFTs need to be nicely aligned with the TGVs. Then you won't see any pattern issues after that. So after the TFT circuitry fabrication is done, the final step is how to open the remaining portion of the glass and then metallize the whole via and connect that to the TFT. So there was a lot of doubts. Now, glass have certain strength. Can this blind via impacting the strength of the glass during this complex TFT fabrication and assembly? So we did some tests. One of the tests is called ball on clamp ring test, where we used to study the surface strength of the glass substrates. So we did different combinations like a bare glass and bare glass and the vias being on the side A and vias being on the side B. And what you're seeing here, the plot shows the failure probability plot, failure probability distribution, which shows the failure probability of the sample and likelihood of their occurrences. You have seen that even though there is slight shift between the two distributions, where like a bare glass versus blind via, but their 95% confidence intervals kind of overlap each other. So we see there is a no significant difference in the strength that we found in A side and B side with the baseline non-pattern substrates. And we also see it's not very detrimental for having a blind VS is not a detrimental for the substrate strength of the panel. Here is the each step results. So blind VS created with 370 micron deep in a 400 micron thick glass. And then we fabricated TFTs on it. So each gate, source, and drain, they are connected to the via. It's supposed to be open after the TFT fabrication. Here we opened the via with the 80 micron opening on the TFT side and 90 to 100 micron opening on the back side, which is connected to the driver board. That's the conformal metal we did for connecting A to B side. So we don't see big issues, even though this whole stack went into the complex TFT fabrication process of LTPS. We don't see any thermal issues or compaction issues with the glass, and we integrated that. Yeah, these are some of the electrical results after we probed the TFTs from the backside. You can see the steps of each, after TFT fabrication and after TGVs are opened, then metallization from the A side and then B side, and then we probe. So the biggest thing is we track the TFT performances at each step of this whole complex integration, and we see there is no or very, very minimal shift in the threshold voltage of the LTPS TFTs when they are driving from front side to the via opening and then metallization of the via and from the back side. So with that, I will go on to the next step. This is for aluminum ribbon ceramic substrates for the 5G millimeter wave applications. This is a lot of people talk about, there is a wireless 4G transition is happening to 5G NR bands, and there are within the mobile broadband from 600 megahertz to 6 gigahertz, you need to have like nearly 50 filters. So it's a lot of filters. Each filter are dedicated to specific resonant frequency, and they have to have a good pass band and a very good band rejection to the adjacent frequencies. So increasing number of bands leads to increasing number of filters in the smartphone, and this is going to be increasing in the coming years. And high frequency operation and broadband and integrated device functionality with the number of filters to be, it means it need to be miniaturization, requires a new substrate with a lower thickness, low energy dispersion loss, and a good thermal management. So for this, Corning innovated a continuous sintered ceramic process, which is basically sintered alumina. It's a very ultra thin form factor. Right now it can be available in roll-to-roll format. And from there, we can dice it up into the wafer format or into the different shapes. And our current capability is to make like a 4-inch width, and can be on the lengthwise, it can be roll-to-roll. So the thickness, we can make 3 different thicknesses now. So 40 micron, 80 micron, and 120 micron is our maximum thickness for this roll-to-roll continuous sintered alumina. And it also very pure alumina, 99%. So it have a very fine grain structure that leads us very good surface strength of greater than 1.2 gigapascal. And we tested with ball and ring test that I showed in the microLED side of the glass testing, and also have a very good mechanical edge after we did laser cutting of these ceramics. Here the plot shows our frequency as a function of dielectric constant and the dielectric loss tangent. So we ran the frequencies up to 60 gigahertz, and the aluminum having a dielectric constant of 10 is constant throughout the frequency range. And even for the loss tangent, it is compared to the different doping or different composition of alumina, our ceramic is having a loss in 10 power negative 4s, and it is very consistent throughout the 60 gigahertz frequency range. And it also have a good thermal management capability, because we did some thermal shock test where we heated up the substrate to 1400 degrees C, and within 15 seconds, it cooled down to back to the room temperature. And the thermal conductivity is, of this substrate with 40 micron alumina is around 38 watt per meter Kelvin. And we also demonstrated making a high density via patterns in this alumina, and used for heterogeneous integration for thermal management, or also for the 5G 3D inductor type of filters that you can fabricate on this. So you need to have a true alumina vias, and we can able to make down to 20 micron via diameter with 2 times of the via diameter, 40 micron pitch. We also tested out a lot of filters fabricated on this with a semi-additive process, and we don't see any addition issues. And we also did additive process like printing on this alumina with a good addition and electrical property. So far, I mean, I've shown the material properties. We have excellent substrate, but we need to show up how actual devices, when it's fabricated on it, how it performs. So here is our comparison of alumina ceramic with the incumbent, like LTCC or laminate or silicon or acoustic substrates and 3D glass IPDs. Alumina have most of them, especially it can beat up everything in terms of thermal, and having a very low loss is a big asset. So we came up to build up microstrip bandpass filters and diplexers and IPDs for the 5G NR bands, especially FR2 band for N257, 258, 259, and 260, which is like maybe 24.2 to 43.5 gigahertz range. So our metrics that we considered was how the performance, especially the insertion loss, will be when compared to the other substrates, and also can we do the miniaturization of the devices that is needed for the broadband wireless application. So we designed the structures which is lesser than the current technology. As you can see, insertion loss for the current technology is less than 3 dB. And we designed the EM simulations with the insertion loss less than 2.2 dB. And also, bandpass filter size is almost half of what's the current technology is. So we fabricated this in collaboration with Georgia Tech, their PRC center, and 4 different test structures we kind of designed in this, especially the 5th order bandpass filter for the NR FR2 bands, which is 3 different topologies: edge couple, hairpin, and interdigital structures. And also we designed diplexers in the same band. And also we did IPDs, which is kind of couple and coupler in coupling with the diplexers. And we kind of seen how the performance is. And here is the top side and bottom side of the 4-inch alumina substrate after the filter fabrication. And you can see the vias are conformally plated. That's an X-ray CT image showing that the white contrast is the copper conformal in the vias. These vias are 40 micron in diameter on A side and 25 micron diameter on the B side. Here is the performance that comparing to the theoretical versus the measured properties of a hairpin bandpass filter and also interdigital bandpass filter for different frequency bands. You can see that the dotted line representing the measured one and the solid line representing the simulated ones, and both very, very good correlation has been achieved in this after filter fabrication is done. This is again for couplers and IPDs. So the design shows there is a couple line coupler, and in contact with the different diplexer there with a different frequency range, N258 and 259. We able to got a good correlation again with the theoretical and the simulated IPD designs. Diplexer's response has been passed through the coupler successfully with both through couplers and also the variant through couple and coupled through the paths. In a nutshell, this is the comparison chart with the incumbent, dry film laminated on the glass versus other filters fabricated on Corning's ARC. Especially, we are looking at the insertion losses there. We are ARC shows a very low loss compared to the dry film low loss dry film laminated on the glass substrates. And also the size, we kind of reduced up to 88% from the actual physical size of the filter. And we got both the insertion loss and the size shows the superior performance filters fabricated on ARC for the 5G and R bands. So this is my summary, last slide. So next generation electronic devices require innovative substrates, and Corning being very, having a lot of expertise on glass science and ceramic science, we are playing a big role and working towards it. And also I showed some of the results related to the integration of metallized vias for the TFT backplanes for zero bezel microLED displays for large area microLED display. And also shared some of the material properties for the aluminum ribbon ceramic. We have a booth there and we showcased the roll-to-roll ceramic. If you have a time, please stop by. Having a very superior strength, and the ceramic is ideal material for RF applications given its impressive material properties. That is my team and collaborators kind of worked on this from the ideation session to the prototype session. So thanking everybody, and with that, thank you everyone, and I can take questions.
Please thank our speaker. Any questions, please?
Hello, Rajesh. Thanks for the presentation. Very good one. You showed the strength of the die with the TGVs, and you showed that even for the bare die or bare glass without the TGV and with the TGV, both having similar strength. How do we understand that?
So you have to understand how the strength plays a role in the glass, especially the strength is detrimental with the flaws in the glass. So when the native surface of any flaw, most of the breakage points is originated from that flaw. So with the etching, what happens is it kind of clears out any flaws that happen on the glass surface. So by creation of that blind via substrates, we etched significant portion of the glass thickness, and any flaws that is on the surface kind of etched out. That creates more strength.
Any other question, please? Thanks again, our speaker. And thanks for joining the session.